Hello everyone and welcome to another class of Physiology for Engineers with Professor Gonzalez-Fernandez at Lehigh University. Today we're going to look at the biomechanics of bone and cartilage. But before we go in depth into each separate tissue, we have to look at some specific and basic concepts that we need to understand in order to understand this lecture. So the first concept that I want to talk about is the stress. So the stress is the force divided by the area, and it's going to be represented here. And then we have the strain. So the stress is a measurement of deformation, so is the change in length. And it's going to represent it here. So we can represent this, the stress and the strain together in a stress-strain graph. So here we'll have the stress, and then here we'll have the strain. And then we'll have here a curve, and then this line is going to have a slope. And the slope is going to be the Young modulus. So the Young modulus is the strain divided by this, is the stress divided by the strain. So it's equal to force divided by area and everything divided by the change in length. Okay. So this is really important. The stress, the strain, and the Young modulus is very important to understand the different concepts that we are going to look at this lecture today. So first, we are going to look at the bone. So the bone, as we have seen in the previous lecture, is a composite. And is formed by two different materials. It's formed by a fibrous material, which is collagen, specifically collagen type 1. And it's also formed by a ceramic phase, which is the hydroxyapatite crystals, the calcium phosphate. So this difference in composition, the collagen and the hydroxyapatite crystals together, they are going to give bone a really specific behavior, which is an anisotropic behavior. So this means that the behavior of the bone is going to be different if we apply force to the bone in the longitudinal direction or in the radial direction, okay? So the Young modulus is going to be different if we apply force in the longitudinal direction. So if the force comes from here, the Young modulus is going to be higher in comparison to if we apply the force in this radial direction, the Young modulus is going to be lower, okay? And this is because here we have in the bone, we have the collagen fibers that are well organized, and these are going to be the reason why the Young modulus is going to be higher when we apply force in this way in the longitudinal direction in comparison to the radial direction, which the Young modulus is going to be lower. So in order to demonstrate easier, I brought with me a human-sized reproduction of a femur bone, which is a perfect example of a long bone. So the femur bone, in this case, is a left femur bone. So it goes from our hip here to our knee here, and is going to connect our upper body to our lower body. And we have the different areas of a femur bone. So here we have the head. The head is going to be connected to the hip and is going to be covered in cartilage. And then here, in this part here, this is the neck of the femur. Then we have the shaft of the femur. And finally, we come here to the knee, which is going to be the part that is linked to the knee joint, and it's going to facilitate the movement of our knee. So here we have the two condyles and then the patella. And this area here is also be covered in cartilage. So the cartilage is needed here on the head and here on the patella in order to allow for really smooth movement in the head and really smooth movement here on the knee. Okay, so if we apply force here on the bone on this direction, so on the longitudinal direction, the yaw modulus is going to be much higher due to the organization of the fibers of collagen in this direction, okay? In comparison, if we apply the force or the pressure here, and we apply it in a radial manner, the yaw modulus is going to be lower. And this is because in this case, the collagen fibers will receive the force parallel to their alignment, okay? And this is very well represented in the stress-strain curve. So the stress and here the strain. If we apply the force or the pressure in a longitudinal manner, we are going to have something like this. And if we apply it on a radial manner, we are going to have something like this. So here we can see very clearly that the slope, therefore the yaw modulus, is higher when we apply the force longitudinally in comparison to the yaw modulus if we apply the force radially, which is going to be lower. And this gives the bone its functionality, okay? Because the bone needs is load bearing. That means that it needs to bear or to support all the weight of our body, right? So the femur is going to support the weight of our body this way, right? The femur needs to support all the weight of our upper body in this direction. So therefore, it needs to be tougher or have a higher yaw modulus in this direction to support all the weight. And another fun fact is like most of the bones are fractured in this direction, so they break really easily when we have like a fracture in this direction, so a hit in this direction. But we are going to look at the fracture toughness in a little bit, okay? So anyway, we need to understand here that the yaw modulus is higher if we apply force in this direction, and this is going to give us the functionality of the bone of load bearing, so bearing or support the weight of our body. So this will be the first characteristic, so the differences in yaw modulus. Then the second thing that I want to look at today is the viscoelasticity of the bone. So bone and cartilage, both of them are viscoelastic. This means that there is going to be a strain, there is going to be a strain rate dependency. So if we plot here, and we plot the stress versus rate, we are going to have here, for example, here when we do 1,500 seconds, 300, 0.1, and 0.01. So here there is going to be the strain and the strain, they are going to be dependent on the rate. So not only on the impact, the force, but also for how long that force is sustained over time, okay? And it gives the bone the viscoelasticity capacity. Also, I forgot to mention here when I was talking about the yaw modulus. So the yaw modulus here, when we apply the force longitudinally, is around 10 to 20 gigapascals. And when we apply the force radially, the yaw modulus is from 5 to 10 gigapascals, which is a huge difference. And if we look at the single components, at the collagen and the hydroxyapatite, the yaw modulus of collagen is around 5 gigapascals, and the Young modulus of the hydroxyapatite crystals is 80 gigapascals. So as we can see here, this Young modulus is much superior to collagen, but is inferior to the hydroxyapatite. And this is because the hydroxyapatite is distributed in individual crystals along the bone matrix. It's not forming a continuous barrier of hydroxyapatite. If the bone was formed by this continuous hydroxyapatite layer, then we'll have a greater Young modulus. Okay, so let's look at the last bone property that I wanted to look at today. So finally, we have the fracture toughness. Okay, so the fracture toughness means how resistant the bone is when it receives an impact and when a crack is created. Okay, so this is a very specific characteristic, and funny enough, is completely different to the Young modulus. So if we have a crack in this direction, the fracture toughness is going to be much lower. So our bone is going to break more easily. In comparison, that if we receive a crack in this direction, in which the fracture toughness is much higher. Okay, so the bone is going to break. More in a more difficult way. So this is because, again, the composition of the collagen fibers and the direction, and the composition of the bone at large. So in the longitudinal way, so if we receive a crack in this direction, so we receive a crack here, the crack is going to travel perpendicularly to the collagen fibers. Okay, so this crack is going to be really quick because it's going to travel in a parallel way to the collagen fibers that are forming the bone. So the fracture toughness is going to be much lower. But in comparison, so let's make this a bit bigger. When a crack starts here, in this radial manner, so when the crack comes from here, the force is the crack is going to come here and is going to arrive to this line here, which is called the cement line, which is very strong. And then the cement line is going to dissipate the energy back to the surface of the bone. So then the crack is going to be expanded parallel to the direction of the collagen fibers. And due to this dissipation of the energy due to the cement line, if we receive a hit in this direction, the fracture toughness is going to be much higher. So these specific properties of the bone makes bone much more resistant to fracture than, for example, ceramic. When you apply or you have like a ceramic cap made of China, you drop it in the floor, the small crack is going to propagate very easily and very quickly. And bone is going to have a much higher toughness, fracture toughness than ceramics, and the fracture toughness is going to be similar to the one in wood or the one in steel. Okay, so I've looked at the different properties that I wanted to focus for bone. So let's look a little bit more in depth into cartilage.